Hi, everyone. This lecture is going to cover Chapter 11, Problems 2. Specifically, I'm going to go through all of Homework 8. I'm going to solve some of them numerically. I'm not going to solve all of them numerically. I'm going to let you do that on most of them. But I'm going to talk about the concepts and the mathematical equations and give you some help on figuring out how to actually approach these problems. And hopefully we'll reinforce some of the ideas we learned in Chapter 11 and really get them down. Okay, so let's get started. The first problem in Chapter 11 was, we have an automobile traveling at 87 kilometers per hour. Note that's not meters per second, that's kilometers per hour. And the tires have a diameter of 63 centimeters. Again, diameter, not radius. We're going to need to convert that into meters per second and into a radius in meters. We'll talk about that in a minute. So the first thing that we're going to figure out is what is the angular speed, omega, of the tires about their axles. And if the car is brought to a stop uniformly, meaning it has a constant negative acceleration in 17 complete turns or 17 rotations of the tires, what is the magnitude of the angular acceleration of those wheels? And then lastly, how far does the car move during the braking? So what is the linear x displacement over that time? Okay, so the first thing we notice is we need to convert that velocity of 87 kilometers per hour into meters per second. And we do this with just good old unit analysis. There are 1,000 meters in 1 kilometer. In 1 hour, there are 60 minutes times 60 seconds, or 3,600 seconds. And this gives us 87 times 1,000 divided by 3,600, or 24.17 meters per second. Now again, we need a radius as well. So we have a diameter in centimeters. Let's put that into meters. That's 0.63 meters. There's 100 centimeters per meter. That's pretty obvious. But we want R, and R is half the diameter. So the radius is half the diameter, which is 0.315 meters. That's just something that Wiley Plus does to make sure that you're paying attention. From there, we're ready to start this problem. We should note one last thing, that 17 complete turns or rotations is equal to, if we multiply this by, there are 2 pi radians in 1 rotation, we get a change of angle of 2 pi times 17, or 2 pi times 17, 106.8. 4 radians. I'm not sure when you actually do this problem, your numbers are going to be different. I'm not sure. You might want to be careful about when you basically round numbers. I would not round till the end. So if it tells you that you're off just by a little bit, it's probably an error. And you're rounding, you rounded too soon, or you rounded too much, or you didn't round enough. Unfortunately, Wiley Plus does some weird things, and that's one of them. So all right, let's go to part A. And part A is, what is the angular speed of the tires about their axis? So here what we're checking is, you need to recall that for rolling without slipping, which is what we're assuming, that there's a constant acceleration, we get that R omega is equal to V, or the radius times the angular velocity is equal to the velocity at that point. And since we're concerned with the point at the edge of the tire, we take the whole radius of the tire, and we want to find omega. Omega is actually what we're looking for. That is simply V over R. As we saw, V was 24.17 meters per second. And if we divide that by our 0.315 meters, we get omega. I'm going to actually do this because I'm going to want it in a second. I get 76.73 rads per second. And remember that your numbers are different. Okay, so I get 76.73 rads per second, and I've answered part A. Part B, though, said that if the car is brought to a stop uniformly in 17 complete turns of the wheel, 17 rotations, what is the magnitude of the angular acceleration, alpha, of the wheels? So remember that we have our change of angle right here is 106.814. So what we're being asked is if omega initial is 76.73, omega final, because it's brought to rest, is 0, and the change of angle is 106.814 rad, then what is alpha? And it should be obvious looking at this that we're going to use our constant angular acceleration equations. Specifically, we have the final angular velocity squared minus the initial angular velocity squared is equal to 2 times alpha times the change of angle. And if I divide this by 2 times change of alpha on both sides, or 2 times change of theta on both sides, and I note that this is 0, I get that alpha is negative omega squared, omega initial squared, over 2 times the change of theta. And I'll let you guys figure out that number. It's negative because it's decelerating, but that's the whole concept here that I want to make sure you guys have down. We can always apply these constant angular acceleration equations to our problems, assuming that the angular acceleration is constant, which it fortunately is in this case. Actually, let me solve that for a number for myself really fast. I get 76.73 times 76.73 divided by 2 times 106.814. I get 27.56 for me with a negative rad per second squared. I'm going to need that in a minute. So for part B in this problem, or part C in this problem, we're asked how far does it move in the x direction from the time it starts braking until it stops. So we want to know change of x, assuming that A is our alpha again. Remember that these rolling without slipping conditions still apply. This is 0.315. We just found that alpha was negative 27.56. And so this is equal to negative 8.68 for me, meter per second squared. Now I want to know what this is. I don't know what the initial velocity or the final velocity is, and I don't know what the time is. But I do actually know that the initial velocity, I found that earlier, was 24.17 meters per second, and the final is 0 because it comes to rest. And much like the equation we just used for angular, we can recall that for linear motion with constant acceleration, v final squared, v initial squared, is 2 times a times the change of x. And we're solving for change of x. Therefore, the change of x is v final squared minus v initial squared over 2a, noting that that's 0 because we end up at rest. We get a negative v naught squared over 2a, and here I would get 24.17 squared. I'm ignoring the negative sign because this is negative as well. 2 over 868, and I get a positive number. In fact, for me, I would get 24.17 times 24.17 divided by 2 times 8.68, which gives me 33.65 meters, or about 100 feet. Okay. So to wrap up this problem, basically this problem was really about converting from angular velocity to tangential or linear velocity. Same with acceleration, and doing a little bit of constant acceleration equations. Nothing too major. I hope that it didn't cause you any problems, but just in case, I wanted to go over it. Let's move on. So this problem here, in the figure here, a small solid, we need to make sure we note that this is a solid uniform ball, is to be shot from point P right here. Okay, so that it rolls smoothly. That tells us that we're going to have rolling without slipping in this problem, which lets us relate omega and V and alpha and A. So they roll smoothly along the horizontal path, up along the ramp, and onto a plateau here. Okay. It then leaves the plateau horizontally and lands on a game board at a horizontal distance d to the right edge. Okay, so in this, we know that this is 4 centimeters, so 0.04. We know that this distance here is 0.015 meters is H2, and D is 0 and 0.06 meters. Okay, and we know that this ball is going to come flying off the end here with some velocity in the X only. And that's the key thing here. So we want to know what speed must it have, the initial speed of the ball, in order for it to land at the point D is equal to 6 centimeters, okay? So this problem really becomes 2 different problems. We're going to deal with the motion here, which is just projectile motion with the initial velocity in the X direction only. And then we're going to do this part, so this is part 1. Then we're going to do this part once we know V final, we're going to use energy to find V initial. We're also going to have to recall that the moment of inertia of a solid uniform ball is 2/5 mr squared. We don't know what r is. We don't know what m is. Hopefully we won't need them. Secondly, we know that because it is rolling smoothly, we know that r omega is equal to v at every point. And lastly, we know that the energy at any point should be mgh plus mv squared over 2 plus I omega squared over 2. And lastly, I forgot, if we need it, r alpha is equal to a. The angular acceleration times the radius is equal to the tangential acceleration at every point. All right, I think we have everything we need to start working on this. So let's do part 1. And redraw this part. We have a projectile that has some V initial, which is only in the X, Vx only. And it's going to land a distance of 0.06 meters from where it begins. And this is projectile motion, okay? And what we want to know is we want to know what V naught is. We also know here that our H is 15 centimeters. So we know that here is 0.015, I'm sorry, 1.5 centimeters. And here is 0 and 0. So the initial X is 0, X naught is 0, and Y naught is 0. Sorry, Y final is 0. Y naught is 0.015 meters. Okay, and this is X final. And as we did way back for week 3 or whatever it is, recall that when you do projectile motion, you simply list X initial, X final, V initial of X, V final of X, although these 2 things are the same. A of x t, y initial, y final, v naught of y, v final of y, a of y, and t. So we know a few of these things, and we want a few of these things. So, and there's a few of them that we don't care about. So x initial, we know is 0, and y initial, of course, is 0. X final is 0.06 meters, and y initial was 0.015 meters, and y final is 0. V initial of x, we're just going to call v. These are both the same though. Let's just call this v, because that's what we want. And this is 0. We don't know this, but we're going to use it in a minute. We don't know this. V initial and V final of y, we know V initial is 0. We don't know what V final of y is, but let's not even deal with it. We know that this is negative g. Obviously, the acceleration is negative g. It's down. I should really not write that negative sign. The negative sign is implied by the arrow. So, okay, going back to when we did projectile motion, I hope you remember this. We're trying to solve for v of x, and v of x, the only equation we have is x final minus x initial over t. That's really the only x equation we have, and we want to solve for v. We know that x initial was 0, so we have x final over t, and we have a value for x final, but we don't have a value for t. So we go to our y equations. This v initial of y being 0 tells us that we should immediately use y initial minus y final is v naught of y times t minus g to the half t squared. This is 0, and therefore, solving this for t, we get that t is equal to y final minus y initial times 2 over negative g, and taking the square root of this. Okay, so note here that y final is 0. So really what we have is that v is x final divided by the square root of negative 2 times y initial over negative g, or 2y initial over g. If I solve this for a number, I get 0.06 over 2 times 0.015 over 9.81, and this is square root of 0.03 divided by 9.81, and then 0.06 divided by that answer is 1.084 or 1.085 meters per second. So I know my V that it launched with, okay? That's what I found here. This was what I was trying to find. And I used the projectile motion equations with constant acceleration. In this case, it was negative g in the y direction to get V. So part 2, I note that part 2 is a problem where I have the energy at A and the energy at B, and I have a change of height here. So H is 0, H at the top was 0.04 centimeters. So this is 0.04 meters. So I have a change of height of 4 meters at B. And all I have to do is note that E at A is equal to E at B, assuming there's no other forces acting besides gravity. Recalling that I wrote the energy at any one point is mgh plus mv squared over 2 plus I omega squared over 2. Furthermore, let's put in, recalling that I for a solid sphere is 2/5 mr squared, and that omega is v over r. I get this is mv squared over 2 plus 2/5 times 1/2 times m r squared. The 1/2 is coming from here, times v squared over r squared. If I cancel my r's and I cancel the 2, what I find is that I get mgh plus mv squared to the half plus 1/5 mv squared. 1/2 plus 1/5 is 5/10 plus 2/10, which is 7/10. So E is going to be mgh plus 7/10 mv squared. Okay, for every point. So now EA, I know that the height at A is 0 and the height at B is 0.04 meters. And I simply write EA equal to EB, or MGHA plus 7/10 MBA squared is equal to MGHB plus 7/10 MVB squared. Okay. Last thing that I need to note is HA is 0. V from the previous, V from part 1 that I found is my VB, and I want to solve this for VA. So if I divide through by m, I can cancel all my m's. And if I multiply through by 10 over 7, what I get is that VA is the square root of 10 sevens times GHB plus VB squared. And that I'll let you guys put numbers in. But there's a lot going on this slide. Mostly it's number one, you need to remember that the energy is the potential energy of gravity plus the kinetic energy of translation plus the kinetic energy of rotation. Okay. And then you need to turn this using rolling without slipping, using that omega is V over R, and that I is some coefficient times mr squared. You get this all in terms of V. That's to eliminate variables, since we don't know what omega is. And in fact, we didn't know what m or r were for the little ball, the little sphere. And it turns out we didn't need to know what they were, which is cool. So once we have an expression for our energy at any point, we simply plug in our variables. And the last part is knowing what your variables are. It's a pretty good problem. It's simple and fast if you know how to do it. If you don't know, it becomes pretty apparent pretty fast that you don't understand concepts of energy. I actually like this problem because it builds on projectile motion that we knew from from the first section of the course. But I think it's a pretty good problem, pretty fun problem. It's not too difficult. It's just a lot of little concepts, which is kind of the whole idea in chapter 11 is we have a lot of little concepts that we have to apply to problems. All right. So problem number 3 is a yo-yo problem. And in this problem, we're given that a yo-yo has a rotational inertia of 97 grams per centimeter. I want to write that down. I for the yo-yo is 972 grams per, or gram centimeter squared. Units of mass times distance squared. The yo-yo has a mass of 128 grams. It has an axle radius of 2.51 millimeters, and the string is 118 centimeters long. The yo-yo rolls down from rest to the end of the string, and then it asks us a whole bunch of other questions. So what we have to know here is this yo-yo starts at the top, it rolls down to the bottom of a string. This distance I'm going to call delta y is 118 centimeters, so 1.18 meters. I might leave it in centimeters. I don't know. I'll get to that when I get there. I'm also going to assume that G is down, and I'm going to assume my A is down. So remember that we had this equation for a yo-yo, that A was G over 1 plus I over M R naught squared. That's straight up from your book. Your book had a negative sign here, and that negative sign implied that the acceleration was going down and Y was up. In this problem, I'm assuming A is down, so my A is positive in this problem. And my Y is also going to be positive downward. Okay, so going down, Y is positive. It's in the same direction as A. Okay. Okay. So we can really fast, sorry, this is an I, we can really fast figure out what this A is. In fact, that's the linear acceleration is right in front of us. R, remember, is axial radius of 2.51 millimeters. In terms of meters, that is 0.00251. But look here, our I is in grams per centimeter squared. So let's put it in centimeters. In centimeters, this is 0.0251 centimeters. If I put this in centimeters, when I take I over mr naught squared, if I is in grams per centimeter squared and mass is in grams and r naught is in centimeter squared, my units are correct. So this is 972 grams per centimeter, or grams centimeter squared, 128 grams, and 0.251 centimeters squared. And all my units cancel, and this just becomes a whole number. For me, this is 972 divided by 128 times 0.251 times 0.251, and I get 120.5. And I'm just double checking. Yeah, I think I'm all good. Okay, so I get 120.5 meters per second, or just 120.5. Putting that in here, so my A is 9.81. 1 plus 120.5, which is something very small. So 9.81 divided by 1 plus my answer is 0.0807 meters per second squared. Okay, that is actually part A. It's simply plug and chug. If you go back through the lecture notes on how we obtain this, you can figure out how we got A using torque and using Newton's equations. However, in the yo-yo problems, it is just this. In a mass rolling down a hill, if the only forces are static friction and gravity, remember this is actually G sine theta, or sine phi, over 1 plus I m r naught squared. So in the case of the yo-yo, phi is actually 90 degrees. It's like an inclined at 90 degrees. All right, so that was part A. What is the linear acceleration? All you had to do was make sure that your units were correct in order to solve for A. How long does it take to reach the end of the string? And then as it reaches the end of the string, what are the linear speed, the translational kinetic energy, the rotational kinetic energy, and the angular speed? We'll talk about those in a minute, but first we need to find out how long it takes to reach the end of the string, okay? And by long, they mean how many seconds. So if we have A is 0.0807, 0.0807 meters per second squared, and we know how far it's going to travel. Remember, this is down, which is a positive distance of 1.18 meters. And we want time, okay? One thing I should have noted, and I didn't, was it starts from rest, okay? So our initial velocity is 0. We assume, again, constant acceleration as it falls, and therefore the change of y is v naught of y times t plus, we're assuming that we're going down, plus at squared over 2. So we're assuming that y initial and y final, and a is down, y initial is 0, y final is 1.18 meters. And we're also assuming g is down, but that was already done in the first part. So we have our a, and solving this, noting that this is 0, we get that t is equal to the square root of 2 times delta y over a. And for me, that is 2 times 1.18 over 0.0807. Let's see what that is. So square root of 2 times 1.18 divided by 0.0807. I get 5.4 seconds. I get 5.408 seconds to be exact. Well, to be more exact. So I have my time. I have my A. That's easy, just like problem 1. All we had to do was find A. So now for C, D, E, and F, what we want for C and D are linear speed and translational, kinetic. So we want V final at the bottom. We want mv final squared over 2. We want I omega squared over 2, and we want omega final. Okay? And we know A and we know T. So if A is 0.0807, if A is 0.0807 meters per second squared, and T is 5.408 seconds, then it's pretty easy to find V. We know that V initial was 0. We know that omega initial was 0. We have, again, we have that V final is equal to V initial plus AT, and we have omega final is omega initial plus alpha T, but we also have that R times alpha is equal to A, and just a quick recall, M and A and R from the problem statement, make sure these are in kilograms and meters now, so our units are consistent. We had 128 grams, so 128 grams is 0.128 kilograms, and R was 2.51 millimeters, 2.51 millimeters, which is 0.00251 meters. So to find V final, we get V final is V naught plus AT. Cancel that, that's easy enough to find. Once you have V final, multiply m over 2 times V final squared, and that is your kinetic energy translation. Okay? Then you can do one of two things. You can either solve this for alpha, because you know A and R, or you can simply use R omega V, so omega is V over R, omega final. You can do it that way if you want. Once you know that, I for the yo-yo is mr squared over 2. It is simply a disk spinning through its central axis, or, and then we want I omega squared over 2, or putting these two things in here, this is actually equal to mv squared, right? over 4. Because omega is v squared over r squared and I is mr squared over 2, you get this. Okay, so you can just compute this from that, and you can compute omega final from that. There's a bunch of ways you can do it. It's pretty simple. I'm not going to spend any more time on that. So that's the yo-yo problem. It's pretty easy because it's basically plug and chug, find the acceleration from the yo-yo equation, and from there, given the right information, you can find out all sorts of things. Okay, it's nothing we haven't done before other than finding the acceleration from that equation that we derived. All right, so let's do some kind of new stuff. This says that there's a force with components negative 7.3 newtons in the I direction and 4.2 newtons in the J, that's acting on a particle with a position R of 3.9 and 6.8 meters in the I and J directions. What is the magnitude of the torque on the particle about the origin and the angle between the directions of R and F? So here we need to know that a torque is equal to R cross F, okay? And if we're assuming that this thing is rotating about here at the point 3.9, 6.8, so this is our R vector. There's a force acting in the negative and positive, so something like this is where our force is acting. And we want to know the angle between R and F, and we want to know what is the magnitude of this torque. If we go back and remember that A cross B in terms of vectors, this is AB sine of the angle between A and B, and it's also equal by the cross product to a bunch of things. Essentially, it's equal to the perpendicular part of each vector multiplied together. So AJ times BK minus BJ times AK in the x hat direction, plus BI AK minus AI BK in the y hat direction, and finally AI BJ minus BI AJ in the k or in the z hat direction. Okay, that's familiar for the right hand rule, but in this case what we want to do is just use this formulation because we have an I and a J, but we don't have a K. So anything with a K goes away, and we're going to get that our vector is A cross B is AI times BJ plus, minus BI times AJ, and it will be in the Z hat direction, which of course that means that this thing, if R points in this direction, F points in this direction, R crossing is a positive rotation. It should be positive, we hope. And it will be in the Z hat direction, meaning it'll come out of the page towards us in the positive Z hat direction, okay? So let's find that really fast. For part A, we want the magnitude of the torque. So that means that we want the torque is R cross F, okay? That means we want specifically IJ, so RI FJ minus FI RJ, and that will be in the Z hat direction. Okay. All right. A couple of things to note here is that the magnitude of R is the square of RI squared plus RJ squared. We're going to need that next. And the magnitude of F is Fi squared plus Fj squared. Simple enough. For the second part of this, we need the angle. And so we note that this RIFJ minus FIRJ in the z hat direction is equal to R magnitude, F magnitude, times sine of the angle between them. And therefore, the angle between them is the arc sine of this RIFJ minus RJFI in the x hat direction over the magnitude of R, magnitude of F. Okay, simple enough. I don't think there's much more to say about this one. It's just practice, really it's just practice with using the cross product, okay? All right, now, in the instant of this figure, this is, I don't know what problem we're on. This is problem 11.29. In the instant of the figure, the two particles are moving in the xy plane, and particle 1, this particle right here, has a mass of 7.44 kilograms and a speed of 7.79 meters per second. It's at a point, D, so let's actually call this R1. D1 of 6.57 meters from the origin, particle 2, 5.56 kilograms, 3.29 meters per second at a distance R2 of 7.64 meters. And we want to know the net angular momentum of the two particles about the origin. So I'm going to change something really fast on this. I want this. So one thing to remember is that a particle has a torque, and the torque is little l, okay? Is the change of little l with t, but little l is actually r cross p, okay? So r cross p here is r crossed with mv. So really it's the mass times r cross v. And for particle 1, we had that we had R1 and we had V1 pointed in that direction. And we were going about the origin. So this is a torque. If we put R and V in, if we multiply this by M, we get MV. If we put R and V in tail to tail, like we normally do for a torque. Okay, remember this is equal to our P vector, our linear momentum vector. R crossing to P is negative. So L for particle 1 is going to be R1, M1, V1 with a negative sign. And then for particle 2, we have R2, which is actually D2. And we have V2, which if we multiply by M becomes P2. Putting these tail to tail, we get R2 and MV2 or P2. This rotation is positive, it's counterclockwise. So L2 is R2, M2, V2, and it's positive. And the only thing that we have left to do is noting that L, the total angular momentum, is L1 plus L2. So L here is R2, M2, V2 minus R1, M1, V1. Okay. A few things that maybe aren't obvious here. The angular momentum is R cross P, R cross the linear momentum. Number 2 is that the total, L total, is equal to L1 plus L2. They just add in summation. And then using the same idea as torques, since they're cross products, you need to figure out if they're negative or positive. It's not very hard at all. It's just a little bit of practice, making sure you understand what L is and how to figure them out as torques. Okay, all right. So now this one is a particle is to move in the xy plane clockwise around the origin as seen from the positive side of the z-axis. Okay, So what that means is if we have an XY plane, okay, Y and X, we're going to have a particle rotating like this in the negative alpha or negative omega sense. In unit vector notation, what torque acts on the particle at a time of t is 8.8 seconds if the magnitude of its angular momentum about the origin is 5.8, 5.8 t squared, 5.8 t to the half, and 5.8 t squared, okay? So, or over t squared. So really, what this problem is saying is two things. Number one, we know that torque is the change in time, the derivative in time of L. And here we're given L is 5.8 kilogram meter squared over seconds, B is 5.8 times t squared, C blah, blah, blah. Secondly, you know that this is going to be in the negative z hat direction, okay? So all we have to do for A, B, and C, and D is take this derivative and we're done, and make sure that we know it. So for example, for A, what is the derivative if L is equal to 5.8 kilogram meter squared per second? So if we take dl dt of this, there's no t. d dt of L is 0 because there's nothing. It's 0 in every direction, x, y, z. For B, and I'll let you do the rest of these, for B, L was 5.8 t squared, kilogram meter squared over seconds cubed, right? If I take the time derivative of this, I get 2 times 5.8, which is 10, 11.6. 11.6 times t, kilograms meters squared over seconds. Squared. Okay. So all you have to do here is take the derivatives. This is going to be in the z hat direction only. In the x and y hat, it doesn't have angular momentum. There was none. There remains none. And so really, once you do that, plug in for t, 8.8 seconds, and you get that L, or I should say, yeah, that the torque, sorry, since the torque at 8.8 seconds is d dt of 5.8 t squared when t is equal to 8.8 seconds. So that is 11.6 times 8.8, which is whatever I get. 11.6 times 8.8, 102.08 in the z hat direction only. That's all pretty simple, just taking some derivatives and then substituting in time, okay? I expect you to know how to do these derivatives. They're just power derivatives. If it helps you to remember that for D, that's the same as 5.8 times t to the minus 2. Okay. This problem's not too hard, I don't think. All right. This problem is a little bit more a physics problem than a math problem. We have a sanding disk with rotational inertia of 1.2 times 10 to the minus 3 kilogram meters squared. And it's attached to an electric drill, and the motor drives it with a torque of 33 newtons per meter about the central axis of the disk. Now, about that axis and the torque being applied for 96 milliseconds, what is the magnitude of the angular momentum and the angular velocity of the disk? This problem is kind of cool. I actually really do like this problem a lot. So we know that I, okay, So I is equal, or that the torque is equal to I alpha, right? And furthermore, because we know that omega final is equal to omega initial plus alpha t, right? We can assume that omega is actually alpha t, right? Or that alpha is omega divided by t. And hence, we get that the torque is I times omega divided by t, or we get that the angular momentum, L, which is I omega, is torque times time. Secondly, the angular velocity, omega, is simply torque divided by I times time. Putting these numbers in for mine, I get 33 times 0.096 seconds, 33 Newton meters. Checking our units, this is Newton meter seconds. Remember that this was M, RV was L, so this is kilograms, meters per second squared, right? And so this is kilograms, meter per seconds times meters times seconds. So one of our seconds cancels and we get kilograms, meter per seconds. So these units are correct. Then checking here, this is 33 Newton meters over our 1.2 times 10 to the minus 3 kilogram meter squared. This is 1 over second squared times seconds, which is 0.096 for me. And again, I get radians per second here. Nothing too hard. I like this problem because you probably would have to think really hard to figure this one out. It's something I didn't cover in the lecture. It's valuable. This right here is a little bit sketchy because this is really change of omega. But okay, we can say it's omega average. And we get our answer. It's a cool problem. It's a fast, easy problem. It's probably more of a quiz question than a full-blown exam problem, but it's a good problem. It's something that you'll probably never forget once you do it, and that's always useful. All right. Rotational inertia of a collapsing spinning star changes to 1/3 of its value. This is problem 11.46. What is the ratio of the new rotational kinetic energy to the initial rotational kinetic energy? So first of all, there's a lot unstated in this problem. We're assuming that L is conserved and L is equal to I omega. L is the angular momentum. So we have I initial omega initial is I final omega final, okay? And we know that I final is equal to I initial over 3. Now these problems are the type of problems that they like to put on things like the GRE, the MCAT, whatever have you, because you have to do some stuff to make some really quick mathematical leaps. Here we notice that I final, or I initial over I final, is equal to omega final over omega initial. I initial divided by I initial third is 3, okay? So we have I initial omega initial squared over 2 is the initial kinetic energy. And we want the ratio of the new kinetic energy. So let me actually back up for a minute. We want the ratio. So we want I final omega final squared over 2 divided by I initial omega initial squared over 2, okay? This is equal to I final over I initial. The 2's cancel, and then omega final over omega initial squared. I final over I initial, right, is the inverse of this. So this is 1/3. And omega final over omega initial is 3 squared. And so we see that this ratio is simply equal to 3. Okay. I really just gave you guys this. There's a little bit of practice on conservation of angular momentum. And because, like I said, it's a good GRE or MCAT or standardized test physics question for whatever discipline you might be in, it's always helpful to have a few of those and to know a few of those. We have 2 more. 11.45, a man standing on a platform that is rotating. So we have some platform that's rotating and we have some guy standing on it, okay? And it has an angular speed omega, and careful here, this is revolutions per second. That means that if we want this in rads, we need to put it in 2 pi rad per revolution per second. Remember that. We'll come back to that. His arms are outstretched. He holds a brick in each hand. The rotational inertia of the whole thing, man, bricks, platform, is initially 6.44 kilograms. And if by moving the bricks, he decreases the rotational inertia, so this is I initial, I final, to 2.58 kilograms meters squared. Okay, we want to know what's the resulting angular speed of the platform. I should also note that this is I. So, and then what is the ratio of the new kinetic energy to the old kinetic energy? I had a student, I'm not going to say who they were, and they made a mistake, which I really want to share with you because it's a really good mistake that some of you might make and then not understand why you're getting it wrong. So from conservation of angular momentum, L initial is equal to L final. And here we can find the resulting angular speed is I initial omega initial over I final. That's pretty simple. However, if you don't remember to convert this into radians, from revolutions to radians, you'll get this wrong. And then from that, the ratio of the new to the old is I initial omega initial. I'm sorry, I did that again. I final omega final squared over 2 divided by I initial omega initial squared over 2. That's easy enough. You'll get this ratio right even if you don't convert to revolutions because the 2 pi squared is going to cancel them both. So the student that I had that contacted me had forgotten to change it to radians and didn't understand why they were getting this part wrong but this part right. You need to convert it to radians per second, not revolutions. It's one of those little unfair things that Wiley Plus does that we just have to live with. Okay, final problem. This is, we've done this before as a ballistic pendulum, but we're going to make sure that we understand, instead of just energy, that we understand it from the point of view of moment of inertia. So in this figure, we have a bullet with a mass of 8.88 grams, and we have a block with a mass of 0.753 kilograms. Note the change in units. That's attached to the end of a 0.2 meter rod. So this distance R is 0.2 meters. And this rod has a mass of 0.671 kilograms, okay? So the block rod bullet system rotates in the plane of the figure about a fixed axis A. The rotational inertia of the rod by itself is, so I of the rod is simply 0.0684 kilograms meters squared. This is for the rod, okay? And then to treat the block and the bullet as particles. What is the rotational inertia of the block, rod, and bullet about point A? Is our first question. Our second question is, what's the angular speed of the system about A just after impact, or if the angular speed is about A just after the impact is 4.28 radians per second. What is the bullet speed just before impact? And so we'll figure that out in a minute. So first things first, point particles. Let me change this to a slightly different slide. So for point particles, we have I is mr squared. The I total of the whole system is going to be I of the rod that was given, plus I of the bullet, plus I of the block, okay? And we were given this I of rod, and we have the mass of the bullet times r squared, plus the mass of the block times r squared. That's easy enough to handle. For the second part, we're told that after impact, the whole system, I total times omega final, where omega final was given as 4.28 radians per second. Okay. The initial angular momentum, though, initially the only thing moving was the bullet. So I of the bullet times omega of the bullet. And so I'm going to move over to here. Omega of the bullet is I total omega final divided by I of the bullet. Okay, so m of the bullet times r squared, where r is the length of the rod. Furthermore, if we want v, I don't remember if the homework asks you for v or for omega. If we want v, we can recall that this is just that. Okay, pretty simple problem. I don't expect it to be too tough. The main concepts here are that you can add the individual moment of inertia to get the total moment of inertia, and that angular momentum is I omega, and that if angular momentum is conserved, the initial angular momentum I omega is equal to the final I omega. Okay, that's all done. I'm probably going to post this weekend a video with some help for homework 9 and some of the practice equations. Know that you can always contact me and we can go through this on Zoom. But I wanted to give you all the chance to get some help with this stuff if you wanted it or needed it. So work your way through it. Remember that your numbers are different, so you're going to need to actually do your math yourself. Hope it all works out. Don't forget, we have tests coming up next week or the week after, depending on what class you're in. So yeah, study, 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 study. Anyway, thanks for watching. I hope you're all well and happy and healthy, and I hope you all stay safe. Talk to you soon. Bye.